writing out answers to your questions, I thought that, you know, everything would probably be communicated better if I, just recorded a little walkthrough. Okay, so first question, could I prove that t of 2n equals t of 2n minus 1 equals n for all n without seeing the recurrence, and what would that look like? So when you say without seeing the recurrence, what I think you're saying is you're talking about like literally writing out the recurrence like this into like literal, numbers plugged in. And that's an absolute yes. You don't need to do this. This is something that I write up for my own understanding, and I put it on here thinking that it might help with you guys too, but it's not actually like part of the proof. It doesn't really prove anything. It just proves for these specific numbers. But what we want to prove is that for any number of n, which we move to k, but right now it's n, any number up to n, this works for, and then what we want to prove is n plus 1, so that we can prove that it's any arbitrary number will work. So yeah, so you don't need to put these actual ones. The other thing that I think you might mean is like this up here, the actual recurrence relation, which that's a great question. Because this problem, t of 2n equals t of 2n minus 1 equals n, reminds me of like those problems that you would see where you have to prove that, this is that problem. You have to prove that, that for any arbitrary number n, if you multiply it by 2 and add 1, you get an odd number. So that, if that's what you mean, yeah, you can prove that, but that's not really what they're asking here. And to prove this recurrence, we do need this recurrence up here. But you don't always need a recurrence for a proof. So, okay. We start with this problem. We plug some things in, and we wind up using this recurrence. And then we get down to here. In what step was this found? I should have went over this better, so I apologize for that. So, as we stated before, we're solving this, and this is what we have initially. T of 2k equals t of 2k minus 1 equals k for any number up until k. So any number up until k, we believe that's done. We don't need to prove that. That's proven, that's accepted. So those numbers equal k. Could be k minus 1, could be k minus 2. If there's a random number n, and we know that n is less than k, then it can go in there. But these numbers here we know are definitely less than k because they are by definition either k or k minus something. So that's exactly what I did to go from t of 2k to this right here. So, okay, I took t of 2k equals t of 2k minus 1 equals k, and then just plugged in k minus 1 everywhere that k was. And that works because we already agreed that anything below k, including k, is proven. It's good to go. So plugged it in. Here we have it. And then just, distributed the 2, simplified it, and this was the equation that I was left with, that we know is true because it's just k minus 1 in there instead of k. So that's where we get this formula. And notice that it is t of 2k minus 2, which equals k minus 1, and we have that. Okay. Any questions on any of this, please let me know, and I will gladly explain. And then this was another good question, to just elaborate on the steps. This is like a bunch of substitutions, and when you see the steps, you might say to yourself, like, you know, why did she pick these substitutions? Like, why? Like, what was the significance of picking, subbing out t of 2k minus 2 for k minus 1? Like, why did she do that? Why would anyone, like, how? And the answer is that it's just like intro to mechanics. Like, you just kind of you just plug things in, and you know where you are, and you know what you want the equation to look like at the end, and so you're just kind of following your nose until you find things that are getting you in that direction. So we start off, we didn't start off here, but that was the last place that we were before there were any questions. So I brought that equation down here, and here we have it. Sorry, I'm reading over my little note. Addition is commutative, yes. So the substitutions I did, you could have done them in any order, but the idea is just that we understand, like, what equals what, so that we can sub things in and out and make the equation look how we want it to look, to conclude our proof. So we know this is what we have, and we know that this is what we want. And the reason that we want to plug in k plus 1 is because we already know that up to and including k is true, and we want to prove that it's true for any arbitrary number. So that means any number above k and any number below k. So whatever. So we do k plus 1. We could do k plus 2, but we're doing k plus 1. So now we manipulate. The first substitution is the one I just went over, where we take t of 2k minus 2, and we're going to sub that out for k minus 1, because right up here we have that, so we can do that. So okay, distribute the negative, and then we have minus k plus 1. So the next substitution picked is going to be a sub out of t of 2k equals k, because we know that this was in our initial formula, so we can just sub that out. So boom, t of 2k equals k, and already this formula is looking like it's gonna be able to prove something for us, but we have this one left that's looking not like what we want. So we sub that out again for k, because still, by this exact equivalence, we can acknowledge that they're the same. So okay, so then we're left with t of 2k plus 1 equals k plus k minus k plus 1, which equals t of 2k plus 1 equals k plus 1. I'd be glad to go over this again, or any other problem. Feel free to reach out, and I hope this is helpful. Thanks.